In this video, we're going to cover section 1.6, sequential first-order reactions. Up until this point, we've primarily looked at single-step reactions. That is, reactions that involve a single elementary step. And we've looked at the integrated rate laws for variations on these single elementary step reactions. However, many chemical reactions occur in a series of steps, in which reactants are transformed into products through multiple sequential steps. So if we consider the following sequential reaction, we have a reactant that is undergoing some transformation to what we'll refer to as an intermediate, and this intermediate then goes on to form our final product. So the reactant decays to form the intermediate I, and then the intermediate undergoes a final decay, resulting in the formation of product P. Species I is known as an intermediate, and intermediates are generally short-lived species. We can detect them spectroscopically, and on occasion we can actually isolate them. But for the most part, these are short-lived species that are formed during the sequence of reactions and then decays to the final product, as we see in this particular scheme. So this sequential reaction scheme involves a series of elementary first-order reactions. As a result, the differential rate expressions for each species can be written as follows. We can express the rate of change of the concentration of A with time as being equal to minus K1 times the concentration of A. And again, recall that the negative sign just indicates whether something is being consumed or formed. And so A is being consumed, it's decaying to the intermediate. When we look at the net rate of change for the concentration of I, so the change in the concentration of the intermediate with time, we now have two terms that we need to express. And that's because the intermediate is involved in the first step, that is the decay of A to I, but the intermediate is also involved in the formation of P. So as it decays, it forms the product P. And so the first term, K1 times the concentration of A, reflects A going to I. So the concentration of I is dependent upon the rate constant K1 and the original concentration of A. Similarly, we can see that I is being consumed or is decaying to product P. And so this occurs with a rate constant K2, which is dependent upon the intermediate concentration. And so we would express that as a minus K2I. And then finally, we can express the rate of product formation. So dP dt is being equivalent to and dependent upon the rate constant K2 and the concentration of the intermediate. And so we can, again, express each of the reactants or products in this series of reaction steps, the sequential first-order reactions. We can express differential rate expressions for each species as shown. Now, to determine the concentrations of each species as a function of time, we have to begin by setting an initial set of conditions. So if we let only reactant A be present at t equals 0, so at time equal to 0, then the following conditions can be stated. That is, that the initial concentration of A is not equal to 0. That is, we have our reactant species. But at that same t equals 0, no intermediate has formed and also no product is formed. Okay, so if there's no intermediate present, of course, we can't form the product because, as shown in our scheme, the only way to form the product is through that intermediate. So under these conditions, the expression for A is the same as what we derived previously, that the concentration of A is going to be dependent upon the initial concentration of A times e to the minus k1t. So this is the exponential form of our first order reaction. Now, this equation for the concentration of A, this can be substituted into the differential rate expression for the intermediate. And so this was our differential rate expression for the intermediate, as we saw in the previous slide. Now we can substitute in for A after invoking these particular conditions and coming up with our expression for the concentration of A. And so you can see we've inserted that here. Now we can solve that particular expression. I'm not going to go through the details of how that is solved. If you wish to learn more about that, we can discuss that during an office hour or a Zoom meeting. But as you can see, we end up with an expression that equates the concentration of the intermediate to a quotient of rate constants. That is, it's a quotient that's dependent upon both K1 and you see in the denominator K2 minus K1, all multiplied by, in brackets, the difference between two exponential terms, one involving K1 and one involving K2, all multiplied by the initial concentration of A. And this is something that we're always after, is to express reactants, intermediates, and products in terms of initial concentrations of our reactant. So primarily we're always looking for or hopeful that we can derive an expression for the product concentration in a particular reaction scheme that is equated to a variety of terms, but more importantly, a variety of terms that include that initial concentration of reactants. And so that's shown here. So now the final expression that we need to come up with is with respect to the product concentration. So the expression for the concentration of the product can be determined using those same initial conditions of the reaction, with the concentration of A initially being equal to the sum of all the concentrations following t equals 0, so t greater than 0. So like we saw previously in some of our integration for other intermediate rate laws, the concentration of A initially will always be equal to the sum of the concentration of A, I, and P. So this is, again, your mass balance, if you will, in a sense. And so we can rearrange this for P. So P is going to be equal to A naught minus A minus I, all the concentrations of those species. Now, if we substitute in for A, that's going to be our exponential term, and I, which we just solved for here, this is the resulting expression that we end up with. And again, this is in terms of both the rate constants K1 and K2. There's exponential terms as well. But more importantly, or as important, we see that it is expressed with respect to that initial concentration of A. Okay, so this can now be described in a graphical form on the next slide. Now, although the expressions for the concentration of I and the concentration of the product look complicated, the temporal evolution in concentration for both these species predicted by these equations are relatively intuitive. So let's look at this particular figure to discuss that in more detail. So if we look at the decay of A, we see that there's this exponential decay as we go from A to I. And we would expect this because these are first order reactions. And we saw that when we integrated a first order rate law, we had an exponential form that we could express for the concentration of A. Also note that as A is decaying, we see the growth of the product P. Although that growth isn't immediate because we first need to form the intermediate before the product can form from the decay of that intermediate. So with the exponential decay of A, we see virtually an exponential rise or growth of the intermediate concentration. But that will come to a maximum value that will start to level off and then decline, because as I is being formed, it will eventually produce the product P. Now, the temporal evolution, that is, this particular curve, will very much depend on the relative magnitude of the rate constants K1 and K2. In the textbook, they refer to these as Ka and Kb, and you can see in the caption that Ka, that is K1 in our example, is 10 times greater than Kb. And so that means there will be that initial growth of I, and that will occur quite quickly and will reach a maximum value that's significant before it starts to be transformed into product. That is, the decay of I is slower than the production of I. And so depending on the relative magnitude of K1 and K2, you will see some variation in this temporal evolution of the intermediate. So if you have any questions about sequential first order reactions, by all means, send me an email. Thank you.